We are the Group 16 with development of novel iron calcium phosphate cement for cancer treatment. I'm Katie Ryer, the group lead.
I'm Jamie Comstock, purchasing agent.
I'm Ethan Pelagic, the technical liaison.
I'm Amber Soncran, the communications specialist.
So this is our video to discuss the group's progress thus far. Our advisor is Dr. Baduri, and we are working with the National Science Foundation.
A little bit of background about our project is it's used to treat cancer, and there are 1,685,210 new cases of cancer each year. Current treatment options usually involve chemotherapy, radiation therapy, hormone therapy, stem cell transplant, and a lot of other very invasive techniques, so we're looking for a less invasive way to treat cancer. Another statistic is there's almost 600,000 people that will die of cancer this year. Chemotherapy uses a variety of chemicals to treat the cancer and has a lot of side effects, including hair loss, fatigue, vomiting, and others. Radiation therapy uses x-rays and other radiation to treat the cancer and has a lot of side effects as well, including sores, difficulty swallowing, bleeding, and infection. Hormone therapy is used to increase the diminished hormone levels in the body. Some side effects include osteoporosis, stroke, loss of muscle mass, anemia, memory loss, and diabetes. Surgery is another option for removing cancer. It has side effects including pain, fatigue, appetite loss, and swelling. The group looked at 3 material options to produce this cement. We considered calcium phosphate, iron phosphate, and a mixture of iron and calcium phosphate. Calcium phosphate, the main benefit is it has a fast setting time, but it's not magnetic and it has low heat production, which is not ideal for this project. Iron phosphate cement has the high heat production and magnetic properties, but it has a very slow setting time. Therefore, the group decided to do a mixture to get the fast setting time and the high heat production and magnetic properties of the cement.
So our progress so far is that we have tested various compounds, but we've gotten less than desired results. With each sample, we've learned to improve the quality of what we were hoping to get out of the sample. And then our last results gave us the best injectability test and the results for the thing, but it's still not desired. So we've created many setting solutions, the powdered solvents, and then we've created multiple different cements just to make sure that we get what we desire. So this is a mixing solution. This just gives you an idea of the chemical reaction that gets created with the setting solution. And then this is just to ensure that we mix it properly and it is fully mixed. In the top left, you'll see our final powder, and this is just us measuring out the powder. And this is our injectability test, where we inject on a time set basis, and we inject, and then we wait, and then we inject again to see the force that we are applying to the sample.
So immediate work that needs to be completed is to continue to optimize the setting time. The next thing that we're going to need to look at is testing the heat production capabilities as well as the biocompatibility and biodegradability of the cement. The ways that we can achieve the better setting time is to manipulate the iron and calcium phosphate ratios as well as manipulate the liquid to powder component ratios. The next thing we're going to be looking at is heat production, and we can develop a test for that using an electromagnetic field to confirm the heat production is at a satisfactory level for our client. Biocompatibility, we're going to need to employ the health science campus in order to grow cells and keep them living on the cement to confirm that they'd be able to grow in the human body. And the biodegradability can be tested using a solution that we have, or submerge the cement into it, and it is comparable to human body fluid, and we can record the degradation of the cement over time.
So for the budget, We're on track as far as money goes and items. We are waiting on the purchasing the magnets just in case we don't need them. But everything is donated by the lab, Dr. Baduri, and the National Science Foundation.
So we're pretty much on track with the timeline, besides that we haven't bought anything, so there's no really a timeline for that. The blue stars indicate the report/presentation milestones. So the next major milestone is the midterm that is due the week of October 24th. The last major milestone is the Design Expo on December 8th. The red diamonds on the chart indicate prototype estimated dates. There was a setback in our initial prototype date, so that has been changed to a goal of getting it done by next week. And then another prototype, the final prototype, will be done by November 21st.
So in summary, the biggest hurdle that we have with this project is to reduce the setting time. All the other testing that we can do hinges on having an appropriate setting time. Without the setting time, there's no way that we can use the product. And while we're continuing to make good progress that is consistent with our timeline, there's still a large amount of testing that we need to do